Hello, today we are looking at confidence intervals for population proportions. What I'd like to do first is to have you recall what we know about sampling distributions for proportions. And if we sketch it out, we can recall that this is going to, if it meets certain conditions, have a normal, we can use the normal approximation, where the mean of the proportion, sample proportions, is equal to the population proportion, and the standard deviation is equal to the square root of the proportion times 1 minus p divided by n. Now, before we can calculate our confidence interval, we need to think about what our conditions are. And so you can think of RIN. So the first one is we need to make sure that we are getting our data in a random method. So data from random sampling, I'm just going to put a line down here. Random sampling or random assignment. We need to make sure that things are independent. And remember, this is especially important for calculating our standard deviation. So for independence, the samples must be independent, or we have to have if we're doing sampling without replacement, we have the condition of 10%, so sample size must be less than or equal to 1/10 of n. And our last one, normal. So for a normal approximation of the binomial, distribution, we have to have n times p being greater than or equal to 10, and n times 1 minus p being greater than or equal to 10 as well. In other words, at least 10 successes and 10 failures. All right, so now we're ready to look at confidence interval. And you'll recall from last day, it is equal to the point estimate plus or minus the margin of error, and so that's equal to our statistic plus or minus the critical value times the standard deviation of the statistic. Now we've got a problem, however, is that in order to calculate the standard deviation as we have it on the left side of our page, we would need to know p. But we don't know the population proportion. So we will estimate it using the sample proportion, p hat. So for our standard deviation, because we're using p hat instead of p, we're now going to give it a new name, so it will become the standard error. So we'll just highlight that. And the standard error, or SE, standard error of the sample population proportion, is going to be equal to p hat times 1 minus p hat divided by n. Now, the next thing we need to look at is what is our critical value. So last day, we looked at the 68, 95, 97 rule. So rather than just using 68, 95, 99.7 rule, we're going to try to be a little bit more precise, and so we can use the standard, the normal distribution, because we've already, using our conditions, we've already concluded that we can use the normal approximation. So in our normal distribution, if we have the mean of 0, we are looking at the area for, let's say, 95%, the area between the positive and negative z's. Now, today, we are going to actually put a little asterisk next to each of those. And what we need to do is to be able to calculate the area on each end. So we can use our normal distribution using the table A, or our calculator. And so first of all, we need to calculate the area of the tails. This should be reviewed for you. So 1 minus 0.95, which equals 0.05, and then divide that by 2 to get the area of one tail. And so we get 0.025. So this area here is 0.025. And so when you use your table or calculator, so that's the area of tail, that gives us our Z asterisk of 1.96. And so the negative one is negative is also 1.96. And so what we need to make note of is that the asterisk indicates that we are talking about a critical value, not the standardized score from data. Okay, so that's the other new thing here. So we're talking critical value. Okay. Yes, it's calculated the same way, but it has a different meaning. Okay, one more thing. Remember, we are using our sample proportion instead of our population proportion, and so when we do our normal calculation, we are also going to use the sample proportion here. So for our normal condition check, it's going to be n times the sample proportion greater than or equal to 10, and n times 1 minus sample proportion greater than or equal to 10. In other words, the frequency of our success has to be at least 10, and so does the frequency of failures. All right, let's have a look at an example.